Welcome to the video on the kinematic equations. In this video, you will receive an overview of the equations as well as example problems to practice using them. The first equation is horizontal displacement, or displacement, is equal to the initial velocity times time plus 1/2 the acceleration times time squared. The next equation is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. And the third, final velocity is equal to initial velocity plus acceleration times time. These three equations are used for objects that have a constant acceleration. Please recall that the equation velocity is equal to displacement over time can only be used for constant velocity or when acceleration equals 0. The kinematic equations are helpful because they're each missing a different variable. This first equation does not include final velocity. The second does not include time. And the third does not include displacement. These missing variables from the equation will be helpful when choosing which equation to use. A golf ball rolls towards a miniature golf hole, assuming the direction toward the hole is positive. If the golf ball starts with a velocity of 2 meters per second and slows at a constant rate of 0.5 meters per second squared, what is the velocity after 2 seconds? So like any other problem, we start with our knowns and our unknowns. We know the initial velocity is 2 meters per second. So V sub O for original, 2 meters per second. It slows at a constant rate of 0.5 meters per second squared. That is the acceleration, and you can note that from meters per second squared. The ball is rolling in the positive direction but slowing down, so the acceleration is negative. And we're looking for the velocity, or the final velocity, after a time of 2 seconds. Next, we draw our picture. Here's the golf ball, rolling with an initial velocity in the positive direction. It will cover some displacement before it reaches a final velocity. That will take a period of time. And if the ball is rolling in the positive direction and slowing down, the acceleration must be leftward. So on your diagram, you must show the direction of the acceleration. Next, we choose our equation. So starting with our base equations, we are looking for final velocity. And please notice that displacement is not a part of our problem. We don't know it and we're not looking for it. So looking for the final velocity, knowing the initial velocity, the acceleration, and time, we can use the third equation. We'll put in what we know. So the final velocity is equal to 2 meters per second plus the acceleration of negative 0.5 meters per second squared times the time of 2 seconds. So our final velocity is equal to 1 meter per second. Notice how this has slowed down. Next example, an automobile starts at rest and accelerates at 3.5 meters per second squared after a traffic light turns green. How far will it have gone when it is traveling 25 meters per second? So again, we list our knowns and our unknowns. We know the automobile starts from rest, or with an initial velocity of 0. So objects at rest are not moving. It's speeding up. In the positive direction, we have a positive acceleration, 3.5 meters per second squared. We're looking for how far it will have gone. That's our variable delta x for displacement. When at the moment it's traveling 25 meters per second. That is a final velocity. So again, we draw a picture. Our car is sitting at a red light, it's at rest. The light turns green and it accelerates forward to reach that final velocity. I've drawn my acceleration arrow in the same direction of the velocity because we are speeding up. In that time, the car has traveled a certain displacement or distance, and that takes a certain amount of time. Next, we must choose our equation. We're looking for displacement when we know the initial velocity, acceleration, and final velocity. Notice how time is not listed as a known or an unknown. So if we go back to our equations, it seems appropriate to use the second equation because we know initial velocity, final velocity, and acceleration. We're looking for displacement, and time is not involved. Again, we know the final velocity, we know the initial velocity, we know the acceleration, and we are looking for the displacement. So we can use this equation. The initial velocity is 0, we start from rest, so that initial velocity squared term can be eliminated. We'll do our algebra first to solve for the displacement, dividing each side by 2 times the acceleration. Everybody should practice putting this in your calculator because there are a couple places that you could make mistakes. If you're going to do this all in one step, please be sure to put the 2 times 3.5 in parentheses on the bottom. This comes out to be 89.3 meters. Moving forward, we will be recording our answers with 3 significant digits. So that's why I chose 89.3 instead of 89.28 meters. That way our answers will all match on the worksheets and will be consistent. So 3 significant digits in our final answers, and if we have to take a few steps to get there. So our final answer here is the car has gone 89.3 meters. We have one more example. A bird is sitting on a telephone wire and suddenly it takes off after a worm. The bird accelerates at 5 meters per second squared towards the worm for 3.4 seconds. What is the bird's total displacement? Starting with our knowns and our unknowns. The bird is simply sitting on the telephone wire, so the initial velocity is equal to 0. The acceleration is 5 meters per second squared, and it takes the bird 3.4 seconds to get to the worm. The unknown is the displacement. So here's my bird. You can really choose how you draw this picture, but I'm going to draw my bird sitting on the telephone wire, right, initially at rest. And he's going to fly, say, downward and to the right to get to that worm. We're looking for that final displacement. This would take a period of time. And he's accelerating towards the worm to reach that final velocity. So we're looking for displacement given initial velocity, acceleration, and time. Looking at our equations, it seems as if the first is the best to use because we don't know the final velocity. The other two equations involve final velocity, so that would require us to do more than one step. The first equation seems the most fitting. The initial velocity is 0, so that term can be eliminated. We put in our known values. No algebra needs to be done. This brings me to 28.9 meters, and we're asked for displacement, a vector quantity. So the bird ends up southeast of where he started.